Today we're taking a look at 3.6 on arguments and truth tables. Last time we took a look at showing the validity of arguments using Euler diagrams. In this section we take a look at testing the validity of an argument with a truth table. This is a little bit more involved than the Euler diagrams. First of all, you assign a letter to represent each component statement in the argument. Then you express each premise and the conclusion symbolically. Finally, you form the symbolic statement of the entire argument. And the way you do this is you form the conjunction of all the premises, that becomes the antecedent of a conditional statement, and the conclusion of the argument becomes the consequent. Then you complete the truth table for the above statement. If it is a tautology, the argument will be valid. If it is not a tautology, then the argument is not valid. And so we have an example here. We have if P then Q, P therefore Q. And as usual, you can see I'm just going to try to... Okay, so we have two premises. So what we want to do is form the conjunction. So here we go. The conjunction of the two premises, if P then Q and P. So we're forming the conjunction of those. That's going to be our antecedent. I'm going to call it the ant. The consequent is Q, which is the conclusion of the argument. And again, so our antecedent is the conjunction of all of these, which is this part right here. Our consequent is the conclusion of the argument, which is the Q right there. So we have our usual four cases. P, true, true, false, false. Q, true, false, true, false. If P then Q, if true then true is true. If true then false would be false. If false then true. Okay, if false then false. So remember, we just have the one case there that is false. Now we want to form the conjunction of the last column we did and the column containing P. True and true would be true. False and true would be false. True and false would be false. True and false would be false. Okay, and finally we want to take, and let me change my color here to yellow. We want to take this column as our antecedent and this column as our consequent. If true, then true is true. If false, then false is true. If false, then true is true. If false, then false is true. So this would be a valid argument. Alright, so now I have one for you to try. And actually I've done part of the work for you in the fact that I've set up the truth table. Let's take a look at how I set that up. Here's our antecedent is going to be the conjunction of these two. So if P then Q and Q, so here's our antecedent. Our consequent is Q, because that's the conclusion of the argument. So we want to look at the truth values of this column to determine if the argument is valid. So what I'm going to suggest is that you pause the recording right now and see if you can complete the truth table. Decide whether the argument is valid or invalid based on the truth table. And then we'll take a look at that. So go ahead and pause the recording now. Start it again when you're done so that we can go through and check the answer. Okay, hopefully you have figured out an answer to this second example. So let's go through it together. If true, then true would be true. If true, then false is false. If false, then true is true. If false, then false is true. Now we want to form the conjunction of, let's see, this one and the Q column. So, true and true is true, false and false is false, true and true is true, true and false is false. Now we have to do the, oops, I want this one. Let's see if I can get a different color. Let's do green. I want to use the antecedent, and this is our consequent. The Q is, whoops, I'm sorry, the consequent should be over here. Let me erase the green there so we're not getting that confused. Okay, our consequent is the P. So, let's go. If true, then true is true. If false, then true is true. If true, then false. If false, then false would be true. So we do have one case that's false, and for that reason, the argument is invalid. So hopefully you got that one right. Now, there are some, and actually we tested a couple of these. We have both valid and invalid argument forms. First of all, we're going to look at the valid argument forms, and we actually did direct reasoning. Up here in the top one, and I believe our textbook calls this modus ponens is another way to describe it. It doesn't matter to me. You can call it direct reasoning or you can call it modus ponens. Now on the homework and the quizzes, they're going to refer to it as modus ponens, so just be aware of that. The second one, that's if P then Q, P therefore Q. And my Q got cut off there. Contrapositive reasoning, this is called modus tollens. In our textbook, you could call it contrapositive reasoning when you write about it on the exam, but for the textbook, for the purposes of the online homework and quizzes, they're going to refer to it as modus tollens. If P then Q, not Q, therefore not P. So basically what it's doing, it's relying on the fact that if P then Q is equivalent to if not Q, then not P. It's equivalent to the contrapositive. So that's the reason this actually works out. So if we have a not Q, we know not P follows. Disjunctive reasoning, if we know we have P or Q and we don't have P, that forces us to have Q. Likewise, if we don't have Q, that would force us to have P. So both of those actually describe the same thing. Transitive reasoning is something that pops up fairly frequently. If P then Q, we know if we have P, we have Q. If we have Q, then we have R. So we know if we have P, then we have R. So that's called transitive reasoning. Now, what we're trying to do in this next group is we're trying to identify